Alright, we're going to work through lesson 12.4. So this is what we are considering lesson 12.4. So the bad news is that we actually have to do some word problems. So there are going to be some word problems in this. The good news is once you kind of figure out the formula and what it is, then all of a sudden it becomes a little bit easier. It's a plug-in type of problem and you just work it out. So percent review. Over in the box on the side there, there's a little bit of review for percents. Alright, so percent review means, percent actually means it is a comparison to 100. So a comparison to 100. And basically what that means is, if you guys remember anything about how to turn decimals into percents and percents into decimals, the idea is I want you guys to remember how to kind of turn them around and fix them from what they are. So if I say 57% and I want you to turn it into a decimal, 57% as a decimal is 0.57. So the 100 should give that away because it has two zeros. So because it has two zeros means that you can actually move it two places to the left or to the right, depending on what you're doing. If you're going from a percentage, and you'll notice that it's a percentage because of the percent sign, so that gives it away. And going from a percent to a decimal, you have to move it two places to the left. If you're taking a decimal and you're turning it into a percent, it's two places to the right, and make sure that you put the percent sign, because that percent sign is actually what tells people that that's a comparison to 100. So the fraction that you're actually looking at when it says 76% is 76 over 100, or 0.76, which is what it is as a decimal. All right. All percents in algebra class have to be turned into decimals in order to be used in a formula. All right. So you either have to turn them into decimals or fractions to use into a formula. So if you were going to use 125% in a problem, you would have to actually change it into a decimal. So you would move it two places, and this would actually be the decimal 1.25. That's the number that you could use in the problem to represent the percentage in the problem. It gets a little harder as you start to move things around. So, for example, this one's a little tough, and the 125 is a little bit, because of where the decimals are and what you have to remember. So, if you're looking at the decimal point 0.004 as a percent means that you're going to move this decimal place two places to the right. So 1, 2 to the right. So this is actually 0.4%. So you have to be careful with that, because there is a possibility that you're still going to have decimals in your percentages. And I know I've said decimal and percent a lot of times, but you're going to see a lot of decimals, you're going to see a lot of that. So knowing which way to move in this case is really important. So in order to kind of see 0.8% as a decimal means that what I always tell people to do is maybe make a note out to the side if you forget which way to go. So if the problem gets a little harder, maybe just refer back to this one. So if you had a percent and you wanted to turn it into a decimal, you had to move it two places to the left. So this one needs to go two places to the left, which means there's going to have to be another zero added. So that means it moves one place in front of this zero, it moves one more place in front of another zero. So you need to kind of make sure that's what you're kind of taking care of. If the problems get a little tricky, then you may want to kind of think to yourself about a normal percentage like 57% or 23% or 45%. Just jot it down on the top of your paper, and it lets you like be able to visualize which way to move the decimal. So in this case, 1.768 as a percent has to go two places to the right. So this is actually 176.8 percent. And if your ending is a percent, I would tell you to write the percent down, the percent sign. If your ending is a decimal, you don't have to. So it's one of those things where um, it's kind of pay attention to where that decimal is. Okay. Next, what we're actually going to start talking about is how these can be useful in kind of the real world. And most of the time, what you're going to notice is with these percentages, a lot of them deal with money. It's just a lot of money problems. So how much does something cost if you charge 7%? All of this other stuff. So this is an example. So many people, you go to college, you have a student loan, you borrow $8,000 for 1 year. The bank will charge you 7% interest on each year of the loan. So if you want to figure out the interest after 1 year, you would basically take the $8,000 and you would multiply by that percentage. Now, we can't use the percentage in the problem, so instead I would have to change the 7% into 0.07 to use in my problem. So you can either use a time sign or parentheses. 0.07 is what I'm going to do. And these are going to be a lot of calculator problems where you have to take a calculator, you actually have to type it in, you actually have to figure it out. So you would take the 8,000 times 0.07 in your calculator, and you're going to realize the bank is actually going to charge you $560 in interest. Now the next question is one of those questions where it's kind of taking into example that you don't pay anything on the loan. So they basically want you to find the total after 1 year, and you're not going to make payments. It's just how much is this going to cost. So the answer is going to be whatever 8,000 is plus the amount of interest that the bank would charge you. So in this case, the total amount of money owed after 1 year is going to be $8,560. And that's nice, and that's easy, and that's not a big, like, really hard problem to think about. That's a 1 year kind of deal, but the issue starts to apply itself is, like, most of us don't pay loans off or pay things back in 1 year. It takes multiple years to do it. It takes, most of your home loans or home mortgage payments are spread out for 30 years. So if you're only doing 1 year, like 1 year is not that bad. But if you had to do this for 30 years, where you'd actually have to take now another number, this 8560, and do it for the second year, and then you'd have to do the new number with the third year, and the new number for the fourth year, and the new number for a fifth year, you keep working down, and you're like, you notice like it keeps growing and it keeps growing, and that's awesome. And that's the amount of money you have to pay, but that also works for your savings accounts, that works for your CDs at banks. So it's also the way you make money. So if a savings account has a 0.02% interest rate, which is tiny, you will still earn money off of that. And some of you who probably already have like a savings account already know that you don't earn a ton of interest money off of that. So what you look for is interest rates that are pretty high. So your parents or your guardians probably have what they call like a retirement account, and in most of those retirement accounts, they can earn anywhere from like 3 to 7%, and 3 to 7% is actually a pretty good amount of money. So if you notice here, like a 7% interest rate on $8,000 is actually going to earn a parent or a guardian like $560 just in 1 year, and that's just doing nothing. That's putting in the $8,000 and actually earning it. Now, if you find a 7% interest rate, it's pretty awesome. So if you're making money on a student loan and on car rates, I feel like they're a little bit lower now. So this number might be a little bit smaller if you go out to look. But these are things you should look at. Like, somebody is lending you money, but you have to pay them more in return. So in order to borrow money, you have to like pay them something. So on the next one, there's another thing called depreciation, and depreciation is if you buy things. So for example, this could be an Xbox One. or an Xbox 360 or something like that. What ends up happening is the value goes down. So you or your parents who buy that Xbox for like $400 is not worth the same $400 that you paid for it. And in a lot of cases, that's immediate. So when you buy that like Xbox at Walmart and you were to go home and start playing it for like a week or two and then decide that you would want a PlayStation 4, you're not going to get somebody to pay you the same amount of money for that Xbox that you bought it for at Walmart. They just, nobody would do that. And this kind of concept is called depreciation. The value of something is going to go down as you own it. If somebody wanted to pay the original amount for something, they would just go out and buy a new one for themselves. So this idea of depreciation happens a lot. There are some things that actually go up in value. So think of when you watch Antiques Roadshow on PBS, because probably none of you watch Antiques Roadshow on PBS. When somebody takes in like an antique table or antique coins or an old toy that they had in a box still, those things actually might increase in value because of what people would pay for them. And there are some things that do that. But most of the stuff that we purchase and we buy goes through a process called depreciation, where the value goes down over time. So in the case of depreciation, and it says, suppose you buy this used car for $8,000, and you estimate the car will lose 7% per year, and they want you to try to calculate this. The amount the car will lose after 1 year is $8,000 times whatever the interest rate is. So that interest rate becomes a percentage, and we want to change it so we can actually use it in a formula. So that percentage changes to a decimal. So it changes to 0.07. And when we multiply that in our little formula, 8,000 times 0.07 is going to be the same number as it was when the bank was charging us money. So it's $560. Now the problem with depreciation is you no longer get to add the 8,000 or the $560 to it. You actually have to subtract the $560 from the 8,000, which gets us, so that new value is 7,440. So that's how much the car is worth after 1 year. Now, here's a little trick. So it says it loses 7% per year, and that's kind of a problem. So per year means that in order to find out what 3 years would be, I actually have to go through 2 years first. So on part C, the amount the car will lose after 3 years, I actually have to take the 7,440 times the same 7%, and multiply it. So when I take 7,440 and multiply it by 0.07, now the number is 520.8. That means I don't lose as much money as I did in year one, and that's because the value of the car is a little bit lower, so it's $7,440 now. So I only lose $520.80. Now, when I take 7,440 minus 520.80, that's going to equal 69.1920. Now the problem is this is year 2. I haven't even made it to year 3 yet. So I'm trying to make it to year 3. So I'm going to change colors, and then we have to do this again for year 3. I actually have to do 69.1920 times 0.07 again. And that's the amount of money that I would lose during year 3, which is $484 and 34 cents. And you're going to have to round that because if you don't round it, we're going to do dollars and cents here. And if you don't round it, it's going to look kind of strange that you didn't do dollars and cents. I would round correctly. So if there's a 5 on there, you have to round this 4 up. But since it was 4 after this one, it rounds to the 4. So $484.34. That's how much the car will lose after 3 years. And notice, it went down each year. You lost $560 the first year. You lost $520.80 the second year. You lost $484 the third year. And it will continue to go down. Now, the amount that the car is worth after 3 years, you all have to take the 69, 19, 20 and subtract the 484.34. So if I take $6,919.20 and minus $484.34, the value of the car after 3 years is worth $6,434.86. So that is your answer for that one. Now you notice there's a lot of calculator work, so you're going to be doing a lot of typing on your calculator. Be careful with your decimal points. Be careful with what you're typing in. It is a depreciation, so you are losing money, so it is going minus. So you need to make sure that you're putting the minus sign in there and taking care of all that. On top of that, if you miss step number 2 here, you're going to ruin step number 3. If you miss step number 3, you're going to ruin step number 4, and so on and so forth. I hope you guys realize just by doing this one simple problem from year 1 to year 3 that there's a ton of steps involved. Like if you were to do this like by each year by hand, it takes a lot of work. So year number 4 would be just that hard, but year number 5 a little bit harder, and you have to do that step every time. You have to take it times 0.07, and then you have to subtract that number every time you do another step. And there's no way to get to step number 10 without going through step number 9, 8, 7, 6, 5, 4, 3, 2, all of those other steps. Can you imagine doing step number 30 for like a house or something and trying to go through steps number 29, 28, 27, 26, 25, 24, 23, 22, 21, 20? I hope you guys get the point. You'd have to go through all of those steps before you actually made it to the end. So my hope is that after doing just that one problem, you guys would say to yourself, I really want a formula to help me out. Okay? I really want a formula to make sure that I can actually work this out. So here is the formula, and this is what we call an exponential growth problem. Now, the exponential growth has 3 parts that you need to know. The number 1 is always going to stay number 1. The y is always going to stay the y. The y is how much the actual thing is going to cost after you get done. So what this ends up happening is the a value, or the number in front of parentheses, is how much you started with. So on our previous examples, the amount that we started with was like the $8,000 or the $7,000 or whatever you bought the Xbox for, $400. Next, the R value here stands for the percent. So it's the percent that it either grows or shrinks, and it needs to be a percentage. So this percentage is going to be like 5% growth or 3% depreciation or something like that. Now, here's the key part. And underline this, highlight it, put an exclamation point. It is as a decimal. Like you are not putting the percentage in the problem, you are putting the decimal in the problem. And then if you want to calculate the time is now an exponent. So this is why this is called an exponential growth kind of problem. The T stands for time. Now, depending on how you're dealing with time, I will usually tell you that it's in years. There are times what they call time is in like the compounded form. So if it loses money every month, this could be in months. If it loses money every week, or if it gains money every week, those kind of options all can change here. So time is just whatever the amount of time it takes to earn that interest rate. So if it takes a month to earn the interest rate, then that time is in months. If it takes years to earn that interest rate, then the time is in years. If it takes 3 days, then the time is in 3 days, something along those lines. So I need you guys to pay attention to that. Most of the time it'll be pretty straightforward, but there might be a trick problem in there once in a while where they tell you that it does something a little differently. All right. Now, the fun game is I'm going to tell you there's a formula for exponential growth, and there's also a formula for exponential decay. And you guys are always going to moan and groan because, oh, I got to remember two formulas. No, here is exponential decay. Everything is exactly the same, except in an exponential decay, you are minusing the percentage. All right, so if you want to do the decimal and you want to highlight it with some exclamation points, you need to do that. But everything is exactly the same. The initial starting amount is there. The 1 is the same number. The time represents the time. It's all the exact same stuff. The only change is if you're losing money, it's a minus. Or if you're losing something, it's a minus. And if you are gaining something, it is a plus. So growth, looking at a plus sign in there. Decay, you're looking at a minus sign. It is the exact same formula. I can't stress that enough. You're just going to change the plus to a minus. So you actually, when you do these problems, you have to read through the problem. So I've got a couple examples. So, and you're not always using money. I like how this says that the functions can be used in other problems other than money. About 175 million people watched movies in the U.S. last year. If the number of moviegoers is expected to rise is a key word, 4% annually, which means it's in years. So your time is in years. Then how many people will be watching in 3 years? So all of these numbers are important to us. The 175 is the starting number that you start with. The 4% is the rate that it's going to grow by. And the 3 years is the amount of time that you want to watch it grow. So here's our formula, and I would suggest that you write it down until you memorize it. It's y equals a, which is the initial amount, 1. The word rise means that this was going to be a plus sign, and then you have the rate, and then the time. You just plug in these numbers. Now, some people always go, Mr. Cole, what do I do with 175 million? Do I need to make that like 175 with all the zeros after it? The answer is no. You don't have to. It's just when you get done, you have to put the word million behind whatever you're dealing with. So in this case, we'll do that. We'll do the y equals 175, and we'll do the 1 plus 4%. Don't put that in as a percentage. Put it in as a decimal. And then put the 3 as the exponent. And I'm going to go ahead and actually do this in the calculator so you guys can see it, not off screen. So when you type this in, I'm going to type it in just like it is. So it is 175 parentheses 1 plus 0.04, and I'm going to raise that. So I'm going to hit the up caret, and I'm going to put a 3 in there. I'm going to hit enter. And it looks like my answer is, let's go 196. Since there was no decimal point to start out here in the 175 million, we'll just keep it like that. So we'll say 197 million people is your answer. So if you want to know how many people will be watching movies 3 years, it's 197 million people. Now, the nice thing is you did not have to do you didn't have to do the first year, you didn't have to do the second year, and then you didn't do the third year. You just typed this into your formula, and it gave you that answer. So that is the nice thing about a formula. It lets you go directly to what you need to go to. All right? Next problem. Italy had a population of 61 million last year. Its population is declining by 0.7% per year. If this pattern continues, what is Italy's projected population? I'm going to write down the formula again. So y is equal to the initial amount, parentheses, 1, take away the rate, and then the time is up there as the exponent. And if I go through and I start labeling stuff, they started with 61 million people. It's declining at 0.7%, so this is the rate. This is the amount of time we're going to put it in. And a keyword is declining. So your job is to plug in everything in there. So y is equal to 61 million. 1 minus the rate. Now, this is where things get to be tricky because you guys forget to change this to a decimal. It has to go 2 places to the left. 0.07. So 1, 2 puts it at 1, 2. So you want to make sure that you're putting that in as a decimal, not as a percentage. So 0.007. And the time is 10 years. Again, I'll plug this one in the calculator so you guys can watch. Let's go clear. So let's go 61 parentheses times 1 minus 0.007. We're going to raise that to the 10th power. We hit enter. So y is equal to, and since there are no decimals in this problem, we'll round this up. 57 million people. Now, if you don't want to write the word million and you don't have to deal with that, you could write 61 million. So you could actually use this number in your problem. 61, 1, 2, 3, 4, 5, 6. So you could actually use that number in there. But the problem is when you do that, you'd have to keep all of those numbers except for the decimals. You'd have to round to a decimal. So in this case, it makes my rounding a little bit easier. It makes everything a little bit nicer. But it takes you directly to the answer. So on your homework tonight, you're going to be using these two formulas. You're probably going to do a little bit of review. Make sure you do the quick reviews and everything. The worksheet tonight is 12.4, which is actually the online bookwork. But I've got the worksheet for you. So make sure you guys are actually working that. So, oh wait, there's one more problem. My bad. So, one more problem. Oh, we're talking about Troy, 10,000 people in 2010. So let's do all this. Troy had a population about 10,000. That's the A value. 2010, question mark, and it's expected to grow 2% annually, which is 0.0212. It says just write the equation. So I'm going to write down the equation. So there is no time. So y is equal to a parentheses 1 plus r to the t. I put a plus sign because it says grow. I put the formula down, and now I have to plug it in. So y is equal to a is 10,000 parentheses 1 plus 0.02, and then the t, you can leave it as a t. You could also make it an x if you wanted to, because it's a variable. You don't know the time yet. And then down here in part D, it says to go ahead and use that equation for 2030. Now the question is you can't just plug 2030 in there. 2030 is the years. The question is what number do I put in for t? Now it says people in 2010 is this equation. After 2010, so how many years is 2030 after 2010? And the answer is it is 20 years. So if you were plugging that number in for your t, your equation would be y equals 10,000 parentheses 1 plus 0.02, and you can add those if you wanted to and make it 1.02 to the 20th power. I will type this one into your calculator. So 10,000 parentheses 1 plus 0.02 raised to the 20th power. And everybody wants to know how far should you round. This problem has no decimals, and it doesn't have decimals because people can't be decimals. Can't have a half a person or 0.47 of a person. So you round accordingly. So this would be, Troy would have 14,859 people in it. Troy would have 14,859 people after 20 years. So again, sorry about that. Your homework is the worksheet 12.4. It's the online bookwork. Make sure you work on it. Make sure you get it done.